Welcome back, everyone. I am playing Christmas music because at the time of my putting this podcast together, it started to snow. So, Merry Christmas, everybody. Let's get started. So the first thing we want to talk about is inertia being a thing. I have two photographs here. One is of our very favorite lunar lander that hopefully you guys are experimenting with on the FET website, and the other is a paper airplane. One of these has a lot of mass, and therefore it has more inertia. Inertia is the ability of an object to resist a change in its either staying or moving. Okay? So we're going to say the ability of an object to resist change in its velocity. Period. Done. So, usually the more mass you have, you will have more inertia. Less mass you have, less inertia. All right, resistance to forces, another word for that is called friction. And friction is it's a force that works against the currently applied force. So if I were to, where'd that friction go? If I were to, let's say, here's my air hockey puck. Okay, I enjoy a good game of air hockey, especially on a burlap sack or a burlap covered table. So let's make sure we have friction down here. In fact, let's play a game of air hockey versus friction. So here I go. And on the burlap sack, by the way. I can't get the glide. You know, you can hit on a air hockey table with that little pillow of air where there's very little friction and no forces working against that air hockey puck, or very few air, a lot less air forces because there's always friction somewhere. I can hit that puck and it's going to go back and forth 5-6 times. It'll slow down eventually because air is also friction, but friction does work against, and it's all these little bumps on the I don't know if you can see those, all the little bumps on that burlap sack. So, a couple things here. Here's a definition. Friction, well, it's not a definition, it's an explanation. But friction increases the inertia of an object at rest. So this object has inertia, and I'm trying to push it, and it just doesn't want to move. Not you, friction. Okay, but once that object is in motion, friction decreases that inertia. So once we're in motion here, that friction is going to slow it down quicker. Okay, so the last thing we want to remember is friction is a force. So if I apply a force in one direction, friction, where'd it go? Come on, force. Here, let's do this. So I'm applying a force in this direction. The friction is going to actually work against it in the opposite direction. So we've got several types of friction. First one is sliding friction. Who's ever done this before? Put on a pair of wool socks and go skating around the house if you have hardwood floors. I know I have. That is, in that case, the friction is very, very small, very, very minimal. There's a lot of good slide between your foot and that floor. But let's say that we put a table here with a lamp upon it. Let's make an orange lamp. Really ugly one. Okay. All right, and you are sliding. What's going to happen when you come up to this lamp? Well, you're not going to be able to turn very well because there's no friction for you to turn. So curling off doesn't work. You're going to have to make sure that you're careful around the house. Where'd my lamp go? I just broke it. Sliding friction, however, works really well when you have to make a lot of cuts and go back and forth. And so if you're a football player or a soccer player, you like our field turf, and I don't know if this is grass or field turf. I can kind of see little nuggets in there. Here, let's put a few in. But there are these little rubber nuggets. But this is a good surface to get lots of sliding friction. And sliding friction is just the friction of two objects rubbing up against each other. Other sources of friction include static friction. That's actually what happened with my air hockey puck. So if I have a puck here and it's sitting there on top of that burlap, I've got to apply a force to overcome the static friction, because two stationary objects have that little friction between them. So trying to push a table across carpet or a air hockey puck across burlap sack. And then finally we have air resistance. And air resistance is just the wind blowing, or when you're falling, the air resistance causes your hair to blow. These are all forces that work against the primary force that's pulling you or pushing you. Now, one thing about rolling friction, and that is, rolling friction, wheels were created to actually decrease the sliding friction. But there's still a little sliding friction between each contact point. So we have these, have this nice tire here. It's a Bridgestone tire. And on this tire we have these little bitty areas for grips. The more area you have that creates friction, the more like corners and edges, means you have more grip. Now this tire doesn't have a whole lot of grip. It has just these little points on the side. But like a snow tire would have a lot more grips. Now one tire that doesn't have a lot of grips, but it does, it needs it too, is a Zamboni tire. Well, a Zamboni, I think we've all seen them before, and it's Zamboni season starting up pretty soon. But the Zamboni is this big tire that drives on a very low friction surface. So what do? They actually have, and you can kind of see it in here, they actually drill studs, little pieces of metal that dig into the ice. So it actually creates a little bit of extra static friction. Well, it wouldn't be static, but it'd be sliding friction. So it digs into that ice and it climbs out of that little hole, and that hole gets resurfaced over so it doesn't even show up anyways. But there's these little bitty studs in these tires. Next time you're at your local hockey arena, look for one. A common form of friction is air resistance. And so if we have a skydiver who's coming in, and he's coming in really close, he's got a couple forces acting upon him in a vertical direction. The first one is gravity. So we're going to draw that in red here. That's F sub G. But he also has all of these small, I'm going to draw this with a really thin line here, all these particles of air that are pushing against him. And this is the air resistance force. And so that is, we'll call that F. Call it usually the up force. We'll make it a little thicker. So call it force up, force of air resistance. Okay. So it's kind of the normal force, but it's more of a air resistance force. But it is working against the force of gravity. Now, when the force of gravity is greater than the force of the air resistance, that skydiver will accelerate, and he'll keep going down, 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 down. So he is accelerating, and he's going faster, but eventually he will hit a point where the force of gravity is equal to the up force. It's opposite to. So the upward resistance force, the force of air resistance. And when that occurs, we've hit terminal velocity. So at that point, we are at a velocity that stays the same. He is no longer accelerating. And yes, the air resistance can be that much because he's going down so fast. He gets to a point where the air resistance is just really, really, really working and pushing back. And so terminal velocity is the velocity reached when the force of the air resistance is equal to the force of gravity. Now, here's our friend Charlie, and Charlie's sitting on a leaf, so we're going to have to kind of make that leaf a little bit, extend it out a little bit. But Charlie is going to be experiencing the forces in all four directions. Okay, so we extend the leaf, and the four forces are going to be, well, he's got he's got gravity. Let's go gravity first. Let's make this a little thicker. Force of gravity. Okay, we also have the upward force, the normal force. We'll just call this force of normal. Okay, the upward force would just be the air resistance in an upward direction. But then he's also got the frictional forces here. So we have force of friction on both directions. Let's make sure he's not sliding around. So these net forces in four directions, and we'll just keep it at four directions. We could go, 6 or 12 or, in all sorts of directions. But right now we're just going to keep it in four. If they're balanced, okay, if F sub G equals F sub N, and if F sub F equals the other F sub F, okay, if all these forces equal, the net force will be 0. And we'll call that 0 newtons. Okay, if they're balanced. Now, let's give Charlie's leaf, let's extend it out here, and let's actually put some wheels on it. So he's, or she, is on this wheelie leaf that's traveling. And we'll say the traveling in this direction. Okay, so let's talk about why does a force that pushes or pull, how can it go at a constant velocity? So let's go through our four forces again. The net forces are gravity, the normal force. We should assume that we're on a surface here, so let's draw a surface. Okay, and the force that we're traveling here, we're just going to say that there's an invisible motor because we have Charlie moving in this direction, so we have a force that is pushing, or in this case it looks like it's pulling. And we'll call this the force of the pull. And we don't put all sorts of little subscripts here, but force of the pull is what we're calling this one. And then there's also the force of rolling friction. So we'll call this F sub F, force of friction. So how does a force push or pull at a constant velocity? Well, constant velocity means acceleration equals 0. And if acceleration is 0, then the forces are all equal. The net forces once again equals 0. So whether it's moving or not, if there's a constant velocity, the net force is equal to 0. Remember that, please. If we're moving or not, if velocity is constant, the net forces are 0. So that means that the force of gravity is being offset by the normal force, and Charlie's not moving up or down. But then what else is happening is we have a force of the wheels of the skateboard that are pushing or pulling in one direction, and we have a frictional force that is equal and opposite in the other direction. And so force going in one direction equals force going the other direction, which means acceleration is 0, net force is 0, velocity is constant. That's all for today. Have a good evening.